Today we'll be doing the integral from 0 to infinity of the natural log squared of x divided by 1 plus x squared dx. And to start off, we could separate this integral. So we could write this as integral from 0 to 1 of the natural log squared x divided by 1 plus x squared, and plus the integral from 1 to infinity of the natural log squared of x divided by 1 plus x squared dx. And for this integral, we'll make a transformation. So we'll go from x to 1 over x, which means that dx goes to minus 1 over x squared dx, and that 1 goes to 1, and infinity goes to 1 over infinity, which approaches 0. So the bounds are from 1 to 0. And so from here is equal to the integral from 0 to 1 of natural log squared of x divided by 1 plus x squared dx, plus the integral from 1 to 0 of the natural log of 1 over x squared divided by 1 plus 1 over x squared times dx, which is negative 1 over x squared dx. So this is equal to the integral from 0 to 1 of the natural log squared of x divided by 1 plus x squared dx. And we could rewrite this as plus the integral from 0 to 1 of the natural log of 1 minus the natural log of x squared divided by x squared times 1 plus 1 over x squared dx. But we know that the natural log of 1 is 0, and then this numerator will end up being the natural log squared of x. So you have the integral from 0 to 1, the squared log divided by 1 plus x squared dx, plus the integral from 0 to 1 of the squared log divided by x squared plus 1 dx. But look, we have twice that integral. This is equal to twice the integral from 0 to 1 of the squared logarithm divided by 1 plus x squared dx. We now have that the integral from 0 to infinity of the squared logarithm divided by x squared plus 1 dx is twice the integral from 0 to 1 of the squared logarithm divided by x squared plus 1 dx. And to start off, we'll notice that the derivative of the arctangent of x is equal to 1 over x squared plus 1. So if we replace that, we have this is equal to twice the integral from 0 to 1 of the squared logarithm times the derivative of the arctangent of x dx. And now we can use integration by parts. So we can let u equal to the squared logarithm, so that du equals 2 natural log of x times the derivative of the natural log of x, which is 1 over x, and dv equals the derivative of the arctangent of x, which means that v equals arctangent of x because you integrated it. So we're going to have 2 times squared logarithm times arctangent of x from 0 to 1 minus the integral from 0 to 1 of v arctangent of x times du. So we have 2 ln x arctangent of x divided by x dx. And as x approaches 0 and x approaches 1, you can see that this limit tends towards 0. And we have twice of negative 2, the integral from 0 to 1 of ln x times the arctangent of x divided by x dx is equal to negative 4, the integral from 0 to 1 of the arctangent of x times the natural log of x over x dx. So we just got done showing that our integral is -4 the integral from 0 to 1 of the arctangent of x times the natural log of x divided by x dx. And we will recall that the arctangent of x is equal to the sum from k goes from 0 to infinity, -1 to the k, x to 2k plus 1 divided by 2k plus 1. And this is valid for -1 to 1. So this is equal to -4 the integral from 0 to 1 of ln of x divided by x times the sum from 0 to infinity, -1 to the k, x to 2k plus 1 divided by 2k plus 1. From here we could exchange the order of summation integration because our bounds are from 0 to 1, but that's within the range of the integral of convergence. So this is equal to -4 the sum from 0 to infinity, -1 to the k divided by 2k plus 1, the integral from 0 to 1 of ln x divided by x times x to 2k plus 1 dx. So it is equal to -4 the sum from 0 to infinity, -1 to the k divided by 2k plus 1, the integral from 0 to 1, x to the 2k plus 1 divided by x is just x to the 2k. So we have x to the 2k ln x dx. And to solve this integral, we'll use integration by parts again. So we'll let u equal the natural log of x, which means that du equals 1 over x dx. We'll let dv equal x to 2k, so that v equals 1 over 2k plus 1 x to 2k plus 1. So we're going to have -4 the sum from 0 to infinity, -1 to the k divided by 2k plus 1. We'll have u times v, so ln x times x to the 2k plus 1 divided by 2k plus 1 from 0 to 1, minus the integral from 0 to 1 of v times du times 1 over x dx. So this is equal to -4 the sum from 0 to infinity, -1 to the k divided by 2k plus 1. And as x approaches 0 and x approaches 1, this will go to 0. We could bring down the -1 over 2k plus 1 constant. So we have -1 over 2k plus 1, the integral from 0 to 1. And again, x to 2k plus 1 divided by x is just x to 2k dx. You write this as negative times negative is a positive, so we have 4 the sum from 0 to infinity of -1 to the k divided by 2k plus 1 squared times the integral from 0 to 1 of x to 2k dx. It's a fairly standard integral. It's 4 the sum from 0 to infinity of -1 to the k divided by 2k plus 1 squared. We'll have x to 2k plus 1 divided by 2k plus 1 from 0 to 1. But that clearly is 4 times the sum from 0 to infinity of -1 to the k divided by, it'll be 2k plus 1 squared times an extra 2k plus 1. So it'll be 2k plus 1 cubed. And then from here, I won't show it, but this sum from 0 to infinity, -1 to the k divided by 2k plus 1 cubed, is a well-known series, and it evaluates to pi cubed divided by 32. So you have that the integral from 0 to infinity of the squared logarithm divided by 1 plus x squared dx is 4 times pi cubed divided by 32. And we know 32 is 4 times 8. So we have 4 times pi cubed divided by 4 times 8. And the 4 is divided to 1, so we have pi cubed over 8. So in the end, we have that our integral from 0 to infinity of the squared logarithm divided by 1 plus x squared dx just evaluates to pi cubed over 8. And this is the final result. Thank you very much for watching.